Composite Materials MSE 5033, and in this lecture we are going to be talking about uh, a variety of things including carpet plots, nanocomposites, recycling, etc. So what are carpet plots? Carpet plots are three-dimensional plots or two-dimensional plots representing three-dimensional data, including, say for example, in this case, this is a representation of how the stiffness of a unidirectional carbon epoxy laminate will change as a function of the test angle relative to the fiber orientation. So for example, if your fiber orientation is all zeros and your test direction is also zero, you're going to be ending up with a property that is close to that of the um, um, rule of mixtures data for the fiber matrix combination. In this case, it's approximately 250 giganewtons per or gigapascals. Okay, but as you get away from the 0-degree orientation, the stiffness of that composite material will start going down and it will be almost close to that of the matrix by itself when your test direction is close to 90 degrees to the orientation of the fibers. And this is represented in this kind of a figure. You can also take a look at the effect of the fiber volume fraction on the permeability of an aligned fiber bundle. Where is this important? It is important when you are going to be taking a fiber bundle and infusing that with a resin system or doing chemical vapor infiltration of the matrix into the composite material. So if your fiber volume fraction starts going up from 40%, then your permeability starts going down and they start becoming smaller and smaller. So which means that if you have gas or if you have some kind of a matrix that will start blocking up those porosities, then your effectiveness of infiltrating the composite material with the matrix starts going down. You also see that the more infiltrations you are able to do, the density starts going up, but beyond a certain fiber volume fraction, you are beyond a certain fill effectiveness, you are probably not going to get very good effectiveness. So beyond 70% fiber volume fraction, you are probably not going to get very good effectiveness, even if you increase the number of infiltrations or number of fills. So you can see that typically especially for polymer matrix composites, we typically like to limit ourselves to about 65%. And beyond that, it doesn't really make much of a difference. We can also look at how the viscosity changes as a function of temperature. So why do we do this? We do this to effectively design the processing parameters for your composite material. So for example, at around 250 degrees Fahrenheit, you have the lowest viscosity, and then it starts going up as you increase the temperature above 350, then the matrix starts becoming completely solid. So the viscosity goes up exponentially beyond a certain point. So you want to limit your curing temperature, in this case, to about 250 degrees Fahrenheit, so that you can have the maximum lowest viscosity possible, so you get the maximum efficiency of fill into the composite material. So here again you can see that this is the cure profile of your composite material. So you take it to about 240 to 250 degrees Fahrenheit. You hold it at that temperature, let the matrix completely infiltrate the composite fabric and completely fill it, and then you take it to about 350 degrees Fahrenheit and hold it for, say for example, an hour to hour and a half, so that the matrix completely gets solidified, and then you cool it down. So this is the curing profile, and this is the viscosity profile as a function of temperature. So we have to develop this for every composite system that we are going to be working with. You can see that depending upon the process, your fiber volume fraction is going to be what is going to be the most beneficial fiber volume fraction. You can see that from this kind of a plot. So you like to have a resin viscosity. You don't want the resin viscosity to be extremely low, but you do not want it to be extremely high either. So depending upon the prepreg, you can see that, for example, your resin viscosity and your fiber volume fraction, say for example 55% in the case of the epoxy prepregs, your fiber resin viscosity is going to be in the 10 to the power minus 1 Pascal second range. But if you start increasing, so in this case the polypropylene glass fibers, you may not have more than 40% fiber volume fraction or 30% fiber volume fraction, because the density of your matrix is going to be pretty high. So you do not want that. So this is the, so from this is called the isopatience curve, and so you define the matrix and the fiber volume fraction such that you get the best fill. So that covers the what are called the carpet plots. So you are going to be looking at a number of different factors as a function of fiber volume fraction and the matrix, etc. So that gives you that that data. Now let us look at what are the design issues related to different kinds of laminar structures. So how do you define a laminar structure? I mean, we talked about that in one of the earlier lectures. So you take fibers that are oriented in one certain direction. So this would be the most common one. So 0 degrees, so which would be the normal to the loading direction. And then you have fibers that are in the 90-degree direction to that, and then again another layer. So this is a 3-layer laminar structure. So 0, which is the 0 here, and the 90, which is a 90 here, and the 0 again in the 0 direction. And 0 would be the angle with respect to the loading direction and the fiber orientation. In a traditional sense, you can have fibers that are oriented. So so it would be pretty difficult for you to make it like this. So what would be the ideal way, what would be the easiest way to do? Easiest way to do would be to take a fiber toe and weave it like a bamboo mat. So in this case, the one fiber toe goes up and down, up and down, up and down like that. And then you have the fibers that are in this direction uh, that is represented here. So this would be called a plain weave. So there is no, it is a straightforward weave. So you have one weave going in the 0 direction and another weave immediately coming in the 90-degree direction. So this is called the 0-90 orientation. You can also have fibers that are, so this would be a three-dimensional weave. So you have fibers in the 0 direction and then fibers in the 90-degree direction, and then you have fibers that are interwoven like this in order to get better three-dimensional properties. But what would be the difficulty you think in this kind of a layer structure? The porosity of this kind of a preform would be very directional. So which means that it will be difficult for you to infiltrate this with a matrix resin. So even though the fibers are going to, the three-dimensional fibers are going to give you good properties that are almost isotropic in nature, you probably do not find this very commonly. The other difficulty is that this kind of a structure, this kind of a preform is going to be very expensive. So a three-dimensional structure is going to be more expensive unless the application specifically asks for it. You probably would not do that. Of course, the three-dimensional structure has certain advantages, like it has got better impact properties than the other structures. So this would be an idealized linear 3D structure. So you have three-dimensional, so you have fibers in all three directions. So this would be 1, and if you rotate that, this becomes B, the B type of structure. But the most common one would be to take uniaxial laminar structures and then you just place them one on top of the other with the fibers oriented in a specific direction with respect to the 0-degree direction. So for example, if you call this 0 ply, and this would be the 90-degree ply because these fibers are exactly at 90 degrees with respect to the 0 ply. Then if you turn it at 45 degrees, so in this case this is turned counter clockwise to the 0 direction, so this would be plus 45, and then if you turn it at 45 degrees in the opposite direction, then it would be minus 45. So if you calculate the properties, you will see that this kind of a structure would be almost isotropic in nature. So in this case, you have 0, 90, plus 45, minus 45. Then you reverse the order in a symmetric manner. So this would be minus 45, plus 45, 90, and 0. And then you bunch them all that together and you compression mold it, and this becomes a, so you don't want to write the whole stacking sequence one after the other. So if this becomes symmetric, then you would say 0, 90, plus minus 45 symmetric. So which means this has got 1, 2, 3, 4 times 2. It has got 8 lamina layers. So this is 1, 2, 3, 4, 5, 6, 7, 8. So this is the 090 plus minus 45 symmetric structure. Now from the calculations that we did earlier, some of the equations that I gave you earlier, you can calculate the properties. So for example, if you have a 090 plus 45 minus 45 layer alone, you can see that the relative stiffness, even though it is only 40% of the 0 degree direction, it is uniform, and it does not matter what is the angle with respect to which you are doing the testing. So this would be, it would be 40% of the 0 degree direction, but it is constant. So that's why this is uniform in all different directions. So which means that this is an isotropic structure. But because it is not a true isotropic structure, we call it a quasi-isotropic structure. So you calculate all that based on the E11 and E22, G12, which is a shear modulus, and the Poisson's ratio in the 1-2 and the 2-1 directions. If you have the 0-90 direction, then at an angle of 0 with respect to the fiber orientation, the 0 orientation, if you test that, it will give you approximately 58% or 55% of the 0 degree direction. If the fibers were all oriented in the 0 direction, if you have a combination of 0 and 90, this is what you would get. But as you turn away the angle with respect to which you are doing the testing, your properties are going to be changing. So it undulates as a function of the testing angle. If your fibers were all oriented only in the 0 direction, then as you change the angle, it keeps changing and it keeps decreasing monotonically. So if you had the 090 plus minus 45, you would get uniform properties, even though it only is about 40% of the 0 degree direction testing angle. It still gives you uniform properties. So as long as you take that into account, you can design using this material. Now you can also see that the fiber volume fraction would make a difference in the mechanical properties. So as I said to you, in the case of polymer composites, we try to maintain a fiber volume fraction of approximately 60 to 65%, whereas in the case of the ceramic matrix composites, we try to retain a fiber volume fraction of around 40%. But suppose your fibers, those are mainly for continuous fiber reinforcement. But suppose you do not take continuous fiber reinforcements, but you are using chop fibers or random short fibers. And as I said to you, the aspect ratio is very important. So if you have an aspect ratio which is equal to the length or diameter. So In order to get the most effective fiber reinforcement, you need an aspect ratio of 100 or higher, and 1000 would be the best, so which is what you would get in the case of continuous fiber reinforcement. So you can see that here. If you have short aligned, those properties are not going to be that great. So if you're going to be aligning all the fibers in the zero direction and doing the testing, as you increase the fiber volume fraction, the elastic modulus or the stiffness of the composite starts going up. Okay. If you have 0.90, then the properties are going to be dropping off from the 0 degree direction. And if you have 30s, or if you have 0.90 plus minus 45, the properties are going to be less, but they are going to be uniform or equivalent in all the different testing directions. So you can actually plot what are called carpet plots. So if you have 65 volume percent fiber carbon epoxy and 0 plus minus 45 90 stacking sequence, depending upon the percent 0 degree plies and the percent 45 degree plies, your properties are going to be different. So from this you can at least get a reasonably good idea of what the mechanical properties are going to be and what are going to be the changes in the properties as you change the testing angle. So this gives you a rough idea of what those properties are going to be, and when you plot all of those properties in one single plot, it is called it's actually a three-dimensional plot of all the properties, and this is called a carpet plot. Mechanical properties are not the only property that you can find using this kind of an approach, but you can get the same for coefficient of thermal expansion. So depending upon the material and its individual thermal expansion coefficients, when you combine the materials depending upon the fiber volume fraction and depending upon the orientation of the fibers, your coefficient of thermal expansion is going to change. So if you want really low thermal expansion coefficient for boron epoxy, you would like almost all the fiber orientation to be approximately 30 degrees. You can see that this is aluminum. It is approximately 24 into 10 to the power minus 6, whereas steel is approximately 12 into 10 to the power minus 6. Copper is 16 into 10 to the power minus 6. So if you have carbon epoxy and if you want really low thermal expansion coefficient, you would like all the fibers to be oriented in the approximately 20 degrees orientation. So that would give you the lowest thermal expansion coefficient for this material. The other property that you may want to sometimes look at is fatigue properties, because most of these components are going to be exposed to fatigue, and you would like to test the material for that. But suppose you do not want to test hundreds of samples and you want to test only a few samples and see how the delaminations are going to take place. What does delamination do to your composite material? Your delamination will reduce the fatigue properties of your composite material. So this is typically done by contrast enhanced X-ray radiography. And how do they do that? They take a solution of iodine and dip the composite material into iodine, and when they expose it to X-rays, if there is a delamination, that shows up on the X-ray plate. In this case, it is 0 plus minus 45 90 degrees symmetric. But suppose by changing that, if you're going to be increasing the delaminations or increasing the um, load, it may start creating a delamination in your composite uh, panel. So that will show up as delaminations here, and this will drastically reduce the both the mechanical properties as well as the fatigue properties of your composite material. But suppose you change the orientation to 90 plus minus 45 0 instead of 0 plus minus 45 90, you change that to 90 plus minus 45 0 symmetric. It will lead to less damage due to delaminations in your material if you look at it from the edge. So sometimes what we would do is we would make the material into a hybrid composite material. So you can combine carbon and glass, carbon as the facies and the glass as the sandwich material. Glass composite material as a sandwich material. You can have that, and that might give you some better properties uh, due to the uh, due to the properties of your composite material. So if you want to tailor the modulus, flexure modulus and the tensile modulus, depending upon the amount of carbon fiber in your hybrid composite by weight, those properties will change. So you can see that from 8% to 16%, there is a 40% jump in your tensile modulus. But by going from 8% to 20%, there is almost a doubling of the flexural modulus. Why? Because carbon fibers are better in flexure than in tension. We want to modify the material such that it has got better fatigue properties. So SN curve represents the fatigue properties of a composite of any material. So if you determine this, and if you plot the SN curve of a hybrid composite material, you can see that if it is 100% carbon fiber, it has got very good fatigue properties. But for glass, if it is chopped glass, it's going to be pretty low. It's even less than 200 megapascals. But suppose you had carbon fiber facings and chopped glass fiber core, then the properties are somewhere in between. So if you want to reduce a cost but still get some reasonably good fatigue properties, then you would have a combination of the hybrid composite, combination of the carbon fibers and the glass fibers. And in this case, you may only be adding about 20% carbon fiber. Now switching gears a little bit, let's talk about nanocomposites. What are nanocomposite materials? Nanocomposite materials are composite materials where one of the reinforcements and one of the ingredients is of nano-sized shape, nano size. So you can have these fibers or the plates of the nano additives added in multiple ways, or included in the composite material in multiple ways. So in this case, if you just jumble them up and you just add them to the composite material, This is just a nanocomposite material with nothing. But suppose you start making the layers of the nano additives separated out and having the matrix infiltrate in between. It is called you're doing what is called intercalation. But suppose you have completely broken up all the agglomerates of the nano additives, then it is called exfoliation. Okay, so you would do that to get better properties than in this case. I mean, this one may even have a tendency to agglomerate, and agglomeration is not a good thing in composite materials. So there are other nano additives other than nanofibers and multi-wall nanotubes and single-wall nanotubes, things like that. So the first kind is clay. Clay is in the form of platelets, and the next kind is nanofibers, which are fibers of nano-sized shapes, but the fibers are all kind of jumbled up all over, all jumbled up and kind of bunched up all together. Or you could have multi-wall nanotubes, which are very nano size. So you can see that here those length are approximately 500 to 40,000 nanometers, which would be approximately in the millimeter scale, but the diameter is only about 1.3 nanometers. So you can see how small they are. And they would have very high tensile strength. But unfortunately, what you will find is that this tensile strength really does not transfer onto the composite material. So these are different ways to calculate the mechanical properties of nanocomposites. Um, in this case, if your fibers are all wavy and things like that, they define what is called a waviness factor and use that to predict the mechanical properties of the composite material. So you can actually predict the Young's modulus of elasticity for your composite material, but what you will find is that this is predicted and you would never get that. And that's because the effectiveness of blending is not extremely high. So sometimes what you would do is you would combine nanoparticles and conventional continuous fibers so that the nanoparticles would go between the carbon fibers or the glass fibers and provide you with good mechanical properties. So here again is a calculation of your composite materials, modulus, mechanical properties, including modulus and which are longitudinal and transverse. You can calculate that, but this is just a calculation and you're probably never going to end up with the same mechanical properties. So what are we coming to here? One of the biggest problems in composite materials is delamination, and especially in mode 1. Mode 1 would be the most the most difficult or uh, the properties that are most critical in nature, because most of the time what would happen is that if you have a delamination like this, you would not even see it. And you have to do non-destructive evaluation, because you can't destructively, I mean, suppose this is a primary structure, you cannot go and check the structure, and you have to assume that the structure looks okay, but actually inside there is a delamination, and that delamination can grow during the actual service and lead to catastrophic failure. So especially if your component is going to be experiencing mode 1 type of a loading mode. So what we have been doing is trying to improve the interlaminar toughness, so that this layer or the chances of this delamination are drastically reduced. So the way we do that is, um, these are the traditional ways to prevent that kind of a delamination. So one is interleaving and the other one is Z-pinning. So you put pins of material inside in the uncured place, or you would stitch the composite material. But it is not the properties are going to be affected in the in-plane direction. So, but good, if you want to prevent delamination, you have to do something like that. But it would be ideal if you don't have to do this, don't have to put these pins or stitch it. So we have come up with ways to do that by adding nanoparticles. And we have added nano clay, we have added carbon nanotubes, we have added graphite nanoparticles, or graphene and graphene oxide, or nanosilica, or is called polyhedral oligomeric silsexoxane, or POS. And we have also tested uh, a functionalized variety of POS, which is called POS grafted natural polymer. So these are used to modify the interlaminar area to provide you with good interlaminar toughness. And the reason for us to choose something like graphene oxide is because it is extreme, I mean, it's very comparable with all resin systems, all epoxy resin systems, wine luster, polyester, etc., etc. Uh, and it is very easily dispersible, because you can even disperse that in ethanol or water. Of course, you don't want to add water, because you do not want to add any kind of moisture to your composite material. Um, the reason for us to use the graphene oxide is because it has got several organic groups that are comparable with the epoxy resin systems. We have another nanoparticle called POS, which is a silica-based cage material. And the advantage is that you can put reactive functional groups at the ends that can then react with the composite material. And what we have recently done is combine the two, combine graphene oxide and POS to come up with a hybrid nanoparticle. Okay. So in our case, we selected 3 different types of pores, and we selected those as a result of their um, expected reactivity towards graphene oxide. And we synthesized graphene oxide using standard synthesis methods, and then we blended that with polyvinyl pyrrolidone, which is water soluble, which is ethanol soluble, and it is also used to disperse carbon nanotubes or graphene type of materials. And we use very little amounts of graphene oxide, and we made the composite this way. So how do we know whether or not our composite material is going to benefit as a result of? So you put that between the layers, and you put a crack initiating layer, and after you apply this nanoparticle between the layers, you want to see how easy or difficult it is for you to separate those layers. That will tell you whether or not you are improving the interlaminar toughness of your composite material. So this is called the double cantilever beam testing in composite materials. So that's a standard ASTM test that you would use for measuring the effect of these nano additives. What we found is that if you did not exfoliate the graphene oxide, they tend to kind of agglomerate in one single area, and that really did not improve any kind of interlaminar toughness at all. But when you exfoliated the graphene oxide prior to adding it in between the layers, what we found was that it gave us very good exfoliation. So a lot of the matrix resin went between the graphene oxide layers, and then it improved the mechanical properties such as the fracture toughness. And this is the equation for the double cantilever beam testing. So depends upon the load, and this is for one particular loading mechanism. And so when you blend these with different kinds of nano additives, what we found is that the higher the nano additive content, but in weight percent, it is only 0.2% by weight of the composite material. It drastically increased the crack arresting load, and not only that, it made it extremely tough material. So what we found is that by adding only 0.0 to 0.16% of graphene oxide or 1/6% of POS, we were able to increase the interlaminar toughness by more than 100%, assuming that the as received material was 100%. We also looked at grafting POS to some natural polymers such as starch, and what we found is that the interlaminar toughness starts going up quite drastically beyond a certain level, and we believe that we have not yet reached the maximum amount that we can add to these composite materials. The advantage with this approach is that it does not really significantly change the flexural modulus of the composite material. So you can see that the addition of different nano additives changes the fracture mechanism on the composite material, especially when you are trying to peel open the composite material which is reflective of something like delamination. So by adding these nanoparticles, we are able to improve the interlaminar toughness of composite materials. Okay, so let me stop here, and I will be taking over the next lecture in the next section.